So now we're going to move into chapter 19, which is voltage and capacitance. First thing we're going to talk about is voltage due to a point charge, before we move into voltages of circuits and things like that, which is more next chapter. So voltage is also called electric potential. But that potential is not potential energy, the way we think about it. Now, energy, of course, is related to electricity, and I'm hoping I get a chance to talk about that, but not for right now. It's more electric potential, and you could think about it this way. If you think about a dam with water in it, well, the water isn't moving, but it has a lot of possible potential energy. If the dam would break, that could cause a lot of damage. And voltage is kind of like that. It's sort of the potential of what something wants to do. So maybe a better way to say it is like a battery has a certain voltage. Well, the higher the voltage, the more charge wants to move, but it's not moving yet. Here's the really nice thing about voltage. It's not a vector. It's a scalar. So although we'll need the Pythagorean theorem and a little bit of trig, we will not need it as much as you did when we needed force and electric fields. So that's really handy. That's why voltage is a lot of times more useful or easier to work with for electrical circuits. So charged particles have a voltage, and a volt is defined as a joule per coulomb. Now this formula may look kind of familiar. It's actually easier than the other formula. Voltage is kQ just over R, not R squared. So voltage does drop off, but it's not an inverse square relationship. So if you have a little proton, you'll have a certain voltage here, maybe 1 volt, and then it'll drop off maybe to 0.5 volts, 0.25 volts, the further and further away you get from that particular charge. So we're going to have a 1 nanocoulomb charge. So here's our charge. It's positive. 1 nanocoulomb. And we're going to be 1 centimeter. That's not very far from that. And it's pretty easy to calculate the voltage or the electric potential. The K is the same K we've always been using. We don't need anything different. If you remember, nano is 10 to the minus 9th, or 1 centimeter, which is 0.01 meters. Now, let's try to be clever here. Let's try and save ourselves some time. 10 to the positive 9th and 10 to the minus 9th are definitely going to cancel. So the good thing about that is the whole top of the equation, the whole numerator, is just 9. So we've just got to do 9 divided by 0.01. And that's pretty high, 900 volts. B is almost the exact same problem. It says, well, let's move 3 centimeters. And let's see what happens there. So V is KQ over R. Everybody okay if I use 9E9? We'll use the computer language. Look at things. But now we're going to be 0.03 meters. And let's see what happens. 9 divided by 0.03, 300 volts. We find that it drops off exactly the way we would expect. Because there's no squareds, it seems to be dropping off pretty linearly. So at 1 centimeter, it's 900 volts. And then at 3 centimeters, I didn't leave myself enough room, it's 300 volts. What do you think it would be at 2 centimeters? It's exactly what you'd expect. It's linear there, 600 volts. Now we want to deal with, well, what if you have more than one charge? And we want the point where the voltage is 0. So how are we going to do this? No problem. -7 nanocoulombs. And then over here, it's going to be 3 nanocoulombs. Now, these are not vectors. And how far apart are they? 10 centimeters. We're looking for a point in between. We'll call it X. These are not vectors. They're scalar quantities. Now, this is negative, and this is positive. So negative and positive will cancel. Let's see what I can do here. Let's call this V1. KQ over R. So K is 9 times 10 to the 9th. Q is -7 times 10 to the -9th. Oh, that's going to be nice. And R is X. That's V1. V2, also going to be KQ over R. So 9 times 10 to the 9th. And the charge is +3 nanocoulombs. That nano is going to work out real nice. But now this distance here will be 10 minus X. And I know I'm leaving it in centimeters. It's okay. I can make it meters if I want, but I think it's a little less confusing if I don't. We want the voltage there to be no volts. We want the effect of the negative charge to exactly cancel the effect of the positive charge. So 0 is V1 plus V2. Or what we could say is negative V1 is equal to V2. And let's see what happens here. So we're going to get negative. Let's see what happens here. And I actually could have left these in variables a little longer. So 7 times 9 is, or negative 7 times 9 is negative 63 over X. Then on the other side, the negative 9's cancel. 3 times 9 is 27 over 10 minus X. 63 over X is 27 over 10 minus X. Did I leave a blank spot? Nope, we'll have to finish it on this slide, sorry. So what we see here is now we've gotten to a point where it's not even a physics question, it's really more an algebra 1. So let's see, 630 minus 63x equals 27x. We'll add the 63 to both sides. Let's see, 27 plus 63 is 90. Oops, there's an x here, excuse me. All I did was cross multiply. So 630 is 90x. Divide both sides by 90. And that point is 7 centimeters. So we find that it's actually further away from the negative charge, but the negative charge is higher. So that's not an unreasonable number. Now, what we're going to look at tomorrow is we're going to start to bring the angles into things. So I think you can see on this slide, all right, this is a straight distance here, but here, we're going to need to find that distance, and the problem will be a little bit more involved, but we can handle it. So that's all for this video.